So hello everyone. So in this video I'm discussing the integrator circuit using op-amp, and I'll cover this topic in two parts. In first part the ideal integrator and second part the practical integrator. And these are the points that I'll discuss in this topic. So let's start with the ideal integrator. So first of all, as we can see, this is the inverting op-amp, right? Input is on the inverting terminal, and this op-amp is ideal. So V0 by Vi is equals to minus R2 by R0. So just simply replace this R2 resistor with a capacitor, and we will get the ideal integrator. So because this is the mere difference between these two circuits, right? This R2 is replaced by the capacitor, and everything is same. So that's how we should relate the inverting op-amp and ideal integrator, because ideal integrator is the, we can say, the application of inverting op-amp. So this is the ideal integrator, means the output V0 should be proportional to the integration of input, right? And this op-amp is ideal means virtual ground concept is valid here. So there will be zero. So whatever current is flowing in this resistor will be flowing in this capacitor, because here this is the 0 ampere current because the op-amp is ideal. So and this current is nothing but the capacitor current. So this is the IC. And what is this IC current? This IC is VIN upon R, right? And the relation between the capacitor current and capacitor voltage is C dVc by dt, right? And Vc in terms of V0 is minus V0, so it will be C d minus of V0 divided by dt. So this is Vi upon R and is equals to minus of C and d V0 by dt. So from here we can see that this output V0 is equals to minus 1 upon RC, and it will be the integration of Vi and dt. So this is the output of ideal integrator. Now this negative sign of this output, it is showing that this output is having a 180-degree phase, right, due to this negative sign. And in this inverting op amp also, we can see that V0 is equal to minus by no into V1. So here also the phase is of 180 degree. So that's also, we can relate this ideal integrator with the inverting op amp, because the input is at the inverting terminal only. So that's why the phase is of 180 degree, and that's how it is an application of inverting op amp. So let's go with the transfer function of the circuit. So transfer function will be V0 upon Vin, right? Transfer function जैसे यहाँ का ये है. So we have to apply a KCL at the inverting terminal. So Vin minus 0 by R is equals to incoming is equals to outgoing 0 minus V0 upon this impedance, that is 1 upon CFS, capacitor का impedance. So sorry. So the transfer function. So Vin upon R is equals to minus V0 upon 1 upon CFS. So the V0 upon K, which is the transfer function, which is equals to minus 1 upon R CFS. So this is the transfer, right? Now the pole zero plot. So as we can see that there is a single pole at origin. Pole zero plot will be simply a pole at origin. From this pole, what we can say about the time constant, right? So time constant is simply infinite or not defined, because the pole is lying at the origin, which represents unstable system or transfer function, because for the stable transfer function the pole should be lying in the left hand side of S plane, right? So that's why it is representing an unstable response. The time constant is proved, we can see that it is infinite, which is not defined, which is representing an unstable response. Now the frequency response of this identity. So for frequency response, we just put S is equals to j omega in the transfer function. So T of j omega is equals to minus 1 upon j omega r in CF. So its magnitude will be 1 upon omega r CF, right? Which is, you can clearly see it is inversely proportional to omega. So if we draw its magnitude plot, so it will be like this. At zero frequency, the magnitude is infinite, and at infinite, the magnitude will be zero. So this will be the magnitude plot, which is of a rectangular hyperbola form is इस तरह से, because this is of y is equals to m by x form. Xy is equals to, this is the rectangular hyperbola form, y is equals to m by x. At zero frequency, the magnitude is tending towards infinite, right? So this tending towards infinite at zero frequency, this is nothing but the known as the low frequency instability, because at low frequency it is becoming unstable. So this is the low frequency instability or low frequency roll off, and this is nothing but the drawback of this ideal integrator circuit. And to avoid this drawback, we use the practical integrator circuit that I'll discuss in the next video. So this is the magnitude plot, right? Now the step response of ideal integrator circuit. So step response, we simply apply a step input here. So this is the step input, and just for simplicity I have taken one the amplitude, so this input is simply ut, right? Now this is the circuit. The resistor, the capacitor. So now what was the output? So output is minus -1 RC and integration VINDD, and let's say for simplicity I have taken just 1 ohm and 1 parameter. So simply it will be minus integration of input, which will be simply integration of unit step, that is minus of RT, right? So the output will be a negative when like this. So the slow walking is 1. Oh, this is the output. Now I have a question here, that what is the time constant of this circuit? It is RC, which is equals to 1 ohm into 1 farad, which is 1 second, right? So is it true that the time constant is 1 second here? Think about it. And if your answer is 1 second, which can be the answer of most of the people, so it is absolutely a wrong answer, because we have already discussed here that the time constant is infinite from the pole zero block also. And let's see from other perspectives. Let's say यहाँ पर this is the 0 volt, so whatever the current flowing in this resistor is simply going in this capacitor, and this current is VIN upon R. So for all time it is a constant current, right? For whatever input, if input is sinusoidal, if input is pulse input, so current will be constant, right? So whenever constant current flows across the capacitor, so capacitor goes in the linear charging mode, which I have already discussed in the previous videos. So it is in the linear charging. Linear charging is unstable response, right? Because the capacitor voltage will be keep increasing like this, so at infinite it will be infinite. So this is the unstable response. So that's why the time constant of the circuit is not defined. For unstable system, time constant is never defined. So we'll simply, our answer should be time constant is not defined or does not exist, right? So this is the good point, that the time constant of ideal integrator circuit is not defined, right? Now the pulse response. So for pulse response, we will apply a pulse input. So now pulse input can be of variety of types. Say if I first take this pulse as, if the pulse is like this, इस तरह का pulse है अगर यहाँ पर, and it is keep repeating इसके बाद, है ना? So if this is the input for the ideal integrator, so what will be the output? So you can guess your output. So say इसका output कुछ इस तरह से होगा क्या, कि इस तरह का एक पैनल, फिर ऐसा, दिस इज द यूनिट स्टेप, तो उसका इंटीग्रेशन रैंप होगा, तो कुछ इस तरह का होना चाहिए इसका आउटपुट, लाइक दिस. सो बट नहीं, इसका मतलब ऐसा तो नहीं होगा इसका आउटपुट, ये क्लियरली पता होना चाहिए कि ऐसा क्यों नहीं होगा। बिकॉज यहाँ पर देखिए कि इंटीग्रेशन है, तो वी नॉट जो है वो बेसिकली फॉर सिंप्लिसिटी आर और सी की वैल्यू तो 1 ओम 1 फैराड है, तो सिंपली वी नॉट इज माइनस ऑफ इंटीग्रेशन ऑफ इनपुट। सो इंटीग्रेशन करेंगे तो बेसिकली इसका एरिया होगा राइट, मतलब पॉजिटिव एरिया, तो इसलिए इसके लिए तो रैम हो गया। फिर ये जीरो, तो इसके लिए इस तरह से आएगा राइट। फिर अगेन एक पॉजिटिव एरिया बट ड्यू टू दिस नेगेटिव साइन अगेन एक रैम ऐसा, इस तरह से फिर अगेन ऐसा, फिर अगेन ऐसा। सो इस तरह का बेसिक इसका ये आउटपुट है इस पल्स के लिए राइट। एंड if we are not comfortable in this form area, so we can simply write its expression signal system के according, जैसे this is the time period इसका, इसके बाद repeat होगा तो this is t, so this is t by 2, this is 3t by 2 and so on, and let's say इसका amplitude 1 volt। सो इनपुट का जो डेफिनेशन हो जाएगा इट इज यू टी, देन माइनस ऑफ यू ऑफ टी माइनस ऑफ टी बाई टू, देन प्लस अगेन यू ऑफ टी माइनस ऑफ टी, एंड उसके बाद ये सिंपली रिपीटिंग है, तो उसको वी कैन राइट इन द समेशन फॉर्म ऑल्सो। जैसे दिस इज द, ये तो रिपीटिंग टर्म है नहीं, उसके बाद ये रिपीटिंग है, उसमें भी प्रिंसिपल वैल्यू इज 5 टी बाई टू, उसके बाद ये सब बिकॉज टी बाई टू के मल्टीपल, फर्स्ट मल्टीपल, सेकंड मल्टीपल, देन थर्ड मल्टीपल, दिस इज द फोर्थ मल्टीपल राइट। और ऑड प्लेसेस फर्स्ट, फिर थर्ड पे, फिर फिफ्थ पे, ऐसे ऑड प्लेसेस पे नेगेटिव साइन। सो सिंपली जब भी ऑड प्लेसेस पे नेगेटिव साइन होता है तो माइनस वन रेस्ट पावर है, दिस इज द एक्सप्रेशन, एंड देन यू ऑफ माइनस ऑफ ओनली टी बाई टू। ये बेसिकली इसका इनपुट समेशन फॉर्म के अंदर एक्सप्रेशन हो गया। सो इसके लिए जब अपन आउटपुट लिखते हैं तो आउटपुट विल बी सिंपली नेगेटिव में इंटीग्रेशन, सो माइनस साइन को बाहर ले लेते हैं और इंटीग्रेशन सिंपली आर ऑफ टी देगा, देन माइनस ऑफ आर ऑफ टी माइनस ऑफ टी बाई टू, and plus r of t minus of t and so on. So it will be simply minus r of t, then plus r of t minus of t by 2 and minus r of t minus of t. So yes, there is a, this is the minus rt with a negative slope of -1, और ये टाइम इंस्टेंट बेसिकली t by 2 है, so स्लोप नेगेटिव -1 है, इसलिए ये भी t by 2 है। फिर उसके बाद दिस इज द t, दिस इज द 3t by 2 and so on, तो इस तरह से that's why it is drawn like this right। So this is how we can go with the pulse response। so ये first pulse हो गया। now और pulse कैसे हो सकते हैं, so pulse can be like this, symmetrical pulse भी इसमें possible है ना, कि ऐसा pulse हो this one, and this is repeating। so इस pulse के लिए input कैसा होना चाहिए, so अब इस pulse के लिए input कैसा होगा, जैसा पहले we were drawing a triangle in the fourth quadrant and repeating। सो इसका जो आउटपुट होगा वो कुछ ऐसा होगा सर, ये ऐसा। फिर अगेन दिस इज, इट इज रिपीटिंग बिकॉज यहाँ पर यू कैन सी दैट दिस इज द पॉजिटिव एरिया, तो इस पॉजिटिव के लिए ये इतना पार्ट जो है दिस इज फॉर दैट, और बिकॉज नेगेटिव साइन है इस वजह से ऐसा बन रहा है। तो दिस यहाँ पर ये, सो इसके लिए बेसिकली ये वाला पार्ट हो गया, फिर ये नेगेटिव एरिया है तो उसके लिए ऐसा पॉजिटिव वाला पार्ट, फिर उसके लिए अगेन इसके लिए ऐसा, और दिस ऑल्सो राइट। तो इसलिए इस तरह का पल्स बनेगा, और इनफैक्ट इसका भी अगर एक्सप्रेशन लिखना है तो लेट्स से इट इज 1 वोल्ट, इट इज माइनस 1 वोल्ट, दिस इज टी बाई टू, दिस इज टी एंड सो ऑन। सो सिंपली वी एन ऑफ टी जो होगा इसके लिए यू टी, देन फिर माइनस का स्टेप चेंज है, एंड माइनस ऑफ टी माइनस टी बाई टू, देन अगेन प्लस 2, और उसके बाद ये रिपीटिंग है। तो इसको भी एक्सप्रेशन समेशन की फॉर्म में कैन राइट लाइक दिस, टू समेशन एन की वैल्यू 1 to infinite minus 1 raised to power n and u of t minus of n t by 2, and that's why the output is integration with a negative sign, so r of t minus of 2 r of t minus of t by 2, then plus 2 r of t minus of t and so on। So it will be minus of, and summation it will be like this, summation was minus 1 raised to power n r of t minus of n right? So इस तरह से for any pulse we can form the output just by writing the expression or from the saying the area. This is the pulse response. Pulse और भी किसी शेप की हो सकता है तो वो we can just simply इस तरह से expression लिख के we can with that, या फिर अगर आप एरिया में कंफर्टेबल हैं, एरिया इस तरह से देख सकते हैं, तो एरिया के फॉर्म में भी जा सकते हैं, राइट? सो दिस इज द discussion for ideal indicator, and in next video I'll discuss the practical indicator circuit. So okay, thank you.